You know, when you think of the brain, you probably picture a solid, dense organ, right? But what if I told you that deep inside there's a hidden architecture? A whole network of interconnected, fluid-filled spaces. Let's explore this critical network, known as the ventricular system. So what are these hollow spaces really? I mean, they're not just empty caverns. They're actually absolutely crucial for cushioning the brain and circulating essential fluid. Let's get into the precise anatomical definition. So anatomically speaking, the ventricular system is a series of cavities that are located within the substance of the brain. This isn't something on the surface. It's an internal system woven directly into the brain tissue itself. And to really get how it's laid out, we've got to go back to the beginning. To understand the why behind the shape, we have to rewind the clock way back to the very beginning of development. Honestly, the adult anatomy of the ventricles makes so much more sense once you see its embryonic origin. It's basically the blueprint for the entire central nervous system. It's kind of wild, but this whole system is basically a leftover from one of our earliest structures. As an embryo, our brain and spinal cord develop from this simple, hollow thing called the neural tube. Well, that open channel inside it, the lumen, it doesn't just disappear. It actually sticks around and evolves into the complex ventricular system we see in the adult brain. And check this out. The system doesn't just stop at the base of the brain. That original hollow tube continues all the way down into the spinal cord. And that remnant is what we call the central canal. So the key thing to remember here is that it's one continuous channel running from your brain all the way down your spine. All right, so now that we've got the origin story down, we're ready for a tour. Think of this next part as a guided journey through the ventricles, pretty much following the natural path that cerebrospinal fluid would take. First things first, let's get our bearings with a map. Okay, here's our roadmap, a sagittal view of the brain sliced right down the middle. We're going to move through this pathway pretty quickly, so keep your eyes on the labels as we go. First, let's get oriented with the landmark labeled 1, the corpus callosum. Now, this is a huge bundle of nerve fibers that connects the two hemispheres. It's not part of our system, but it's super important because it sits right on top of where we're going to start. And our tour officially kicks off right here at 2, a lateral ventricle. These are the biggest ventricles by far, and there's one in each hemisphere of the brain. This is where our journey begins. Okay, from those big lateral ventricles, fluid flows into this thin, slit-like chamber right in the midline. That's 3, the third ventricle. From there, everything has to squeeze through this really narrow channel you see at 4. That's the cerebral aqueduct. Think of it as a critical bottleneck in the entire system. And that aqueduct opens up into our final chamber within the brain, this sort of diamond-shaped space labeled 5. This is the 4th ventricle, and it's nestled right between the brainstem and the cerebellum. So, we've hit all the major spots on our tour. Now, let's connect all the dots and see how this whole pathway concludes and ties right back to its embryonic origin. And this is where it all comes full circle. See, the 4th ventricle doesn't just hit a dead end. It narrows down at its lowest point and actually becomes continuous with the central canal of the spinal cord. Yep, the very same channel we were talking about from the embryonic neural tube. The entire system is one connected piece. So, let's do a quick recap of the complete pathway. Fluid moves from the big lateral ventricles into the midline 3rd ventricle, then it flows down that narrow cerebral aqueduct into the 4th ventricle, and finally continues on as the central canal in the spinal cord. Simple as that. Okay, so we've just mapped out this incredible plumbing system inside the brain. But you gotta remember, this system isn't static. It's a dynamic, constantly flowing pathway. So the really crucial question to think about now is, what are the consequences if this carefully constructed pathway gets blocked, especially at a narrow point like the cerebral aqueduct? What happens when the fluid can't flow?